Before we get started, I just want to draw your attention to our objectives for today. Okay, I like to start here every time. Today we're going to be distinguishing between atoms, elements, and compounds. So by the end of class, you should be able to look at a substance and tell me if that substance is an atom, an element, or a compound. Now, obviously, a lot of this is microscopic, so I don't mean literally look at an object, but if I gave you a description of it, you would be able to tell me. Then we're going to be comparing and contrasting some things. So we're going to have the terms intrinsic and extrinsic properties, so you'll know the difference between those. Then we'll have physical and chemical properties as well as physical and chemical changes. So being able to tell the difference between each of those. And then the last thing we're going to do is we're going to talk about mixtures and substances. And I have a handy little flow chart to help you work through to figure out if you have a mixture or a substance. And if you do have a mixture, what type of mixture? If you do have a substance, what type of substance? All right. So if we get to the end of class and you're like, I cannot do that, then check in with me and we'll identify which one you're struggling with. This is the stuff that the homework is over, so the questions will be related back to these objectives. So if you get stuck on a homework question too, I can help you with that. Depending on whether or not we get all the way through the notes today will determine if I assign the homework. If we don't get all the way through them, then I'll wait until tomorrow and then I'll assign the homework tomorrow. Sound good? Okay, we'll launch right in. Can you guys see the board okay, or do I need to dim the lights? Okay. All right, so we have here a table. You have the table at the top of your notes. Let's start with just the atom section. So go ahead and you can just type that definition in for me. Atoms are the smallest unit of an element that maintains its chemical identity. Okay? So you may have heard of atoms as the building blocks of matter, the things that are built out of, okay? So there are atoms of many different types, and of course I don't have my periodic table hung up yet, so I'll just pull down my lovely pull-down periodic table. Okay. There are approximately 118 different types of atoms because an atom maintains the chemical identity of that substance. So an atom of silver right here is going to maintain all of the chemical and physical properties of silver. So silver is a shiny reflective metal. It conducts electricity. So those atoms would maintain those properties even as atoms. An atom of silver is going to be different chemically than an atom of neon. Okay. So I like to draw little doodles, so when I am thinking of an atom, I'm just thinking of one little particle. Okay. Then next to atoms, we have elements. They're connected to each other because an element is a pure substance that can't be broken down into simpler, more stable substances. And elements are made up of atoms, all of one element. So you might have multiple atoms, but they're all going to be of the same element. And as we launch further into chemistry, we'll break down what atoms are built of and how you can tell the atoms of different elements apart. But for right now, all you need to understand is that an atom of silver is different than an atom of hydrogen, is different than an atom of plutonium. And then the final type here is a compound. So compounds can be broken down into some simpler substances because they are made up of atoms of multiple different elements. So you might have an atom of sodium along with an atom of chlorine. This can be broken down, as you can see, because we could break it down into atoms of sodium and atoms of chlorine. So this substance can be broken down into a simpler substance. Okay, get rid of my little drawing there so we can move on. So as we're talking about substances, the way we identify what a substance is by its properties. Okay? There's going to be two types of properties that we're going to discuss today. The first one is an extensive property. So an extensive property depends on the amount of matter. Okay? For example, volume. Okay? If I have a larger amount of a substance, if I have more matter, then the volume is generally speaking going to be larger. Or you could think of this as mass, right? If I have more salt, that salt has more mass. The mass changes depending on how much salt I have. Same thing for amount of energy or size. Okay? If I have more hay, then the hay bale is probably going to be larger. So it depends entirely on how much of that substance you have. Whereas an intensive property is the opposite of this, where this is a property that's going to stay the same no matter how much you have. For example, the melting point. Okay? It doesn't matter if I have 100 gallons of water or a teaspoon of water. The temperature at which water goes from ice to liquid doesn't change. So having more water isn't going to change what temperature that happens at. Okay? Whereas having more water would change the mass. So that's your difference between an extensive and an intensive property. Other examples of intensive properties are melting point, boiling point, density, electrical conductivity, heat conductivity, magnetism. Okay? So something doesn't become magnetic suddenly because you have more of it. It's either magnetic or it's not. All right. Now let's talk about physical versus chemical is what your table has. So starting off with physical, these are properties that can be observed without changing the material in any way. So I should be able to observe these properties by simply picking up the object, looking at the object, touching the object, those types of things. These are properties like color, the mass of the object, right? I can put an apple on a scale and get its mass without having to change the apple in any way. Magnetism. Chemical properties are the flip side of this. In order to measure a chemical property, you have to change that substance in some way or another. Flammability is a good example of this. Okay? I like to tell people, if I went on a super cool interstellar mission and I came back with a substance from another planet and I handed you that substance that you had never seen before and asked you, is this flammable? How would you figure that out? Yeah, you would have to try starting it on fire. You've never seen this object before. You don't have any idea about it. And we can't tell if an object is flammable just by looking at it. Now, some people always try to tell me, well, that's not true. I can look at a chair and tell you if that chair is going to burn or not. And I say yes, but only because of previous life experience. Only because you have in your brain knowledge that somebody else gave you that chair is flammable or is made of a flammable material. But if it was a brand new material that you had never seen before, you would have to try to light it on fire before you would be able to tell me if it was flammable. That's the difference between a physical property and a chemical property. You would be able to look at my mysterious outer space object and tell me its color. You would be able to tell me its mass by putting it on a scale. But in order to figure out if it would burn, you would have to physically light it on fire. And the problem about burning is that when you burn something, you change what it is. Wood turns into ash, right? Wood and ash, you would say, are very physically different, right? So it's a different substance which means we have had to change this material in some way in order to tell if this property is true for it. Some other examples of chemical properties are light sensitivity and reactivity with oxygen. So you may have seen hydrogen peroxide, for example, always comes in a dark brown bottle. And that's because hydrogen peroxide is light sensitive. If you expose it to light, it starts breaking down. The same thing is true for many different substances and how they react with oxygen. Okay? If you leave a bicycle outside for a long time, you will notice that over time, that bicycle begins to rust. Believe it or not, the reason it's rusting is just because it's come in contact with oxygen. Okay? So there are many substances that have these chemical properties, but again, the main point here is that we can't tell the difference between them until we try to figure out the chemical property. We have to change it. As soon as you expose hydrogen peroxide to the air, it begins to break down and it's no longer hydrogen peroxide. It has different chemicals in it. All right, to go right along with physical and chemical properties, we're going to talk about the difference between a physical and chemical change, and they're very similar. A physical change, the substance remains the same, but it is changed, but you didn't change what it is. I know that sounds crazy. So examples, cutting, right? I've changed the shape of the paper, but it's still paper, right? So you should have the same substance, which means it should have all the same physical and chemical properties it had before. It should have all the same chemical properties it had before. Some of its physical properties might have changed, like shape or size, right? If you cut something up. Melting something, okay? This is one that confuses a lot of people because our brains tend to think about melting as something becoming a new substance. But if I take an ice cube, it's made of water, H2O. If I melt that ice cube, so it's a liquid, still made of water, H2O. So what the substance is hasn't changed. It's just gone from being a solid to being a liquid. A chemical change, on the other hand, causes the substance to change form. So we are going to have, and you can put this on here, you can write it in big bold letters, you should have a new substance at the end of a chemical change. Should be a new substance. Okay. Examples, burning, oxidation. Okay? Oxidation is the fancy word for rusting. You should have a new substance. When I burn a log, it goes from being wood, which is flammable, to ash, which is no longer flammable, right? If you've ever tried to start a fire in a fireplace that just has ashes in it, it doesn't work very well because those ashes are not flammable. They have new chemical properties, which is a good way to tell that they are not the same substance as the wood. So, things to look for. If it's a physical change, all of its chemical properties should be the same. Might have changed shape or size or volume, but it should have the same chemical properties. If a chemical change has taken place, then we have new substance at the end with different chemical properties than what it started with. So, when we lit the methane bubbles on fire, was that a physical or chemical change? Chemical. Okay? A good clue to us is that burning, the ability to burn, is a chemical property, and so when we lit them on fire, the methane would have become likely oxygen and carbon dioxide, which is why it was difficult to see, because methane is colorless and so are carbon dioxide and oxygen. However, you would have noticed if we just left the methane gas running, you would have smelled it, whereas once we burned it up, you wouldn't have anymore. All right. So since we talked about melting being a change of state and that being only a physical change, I think it is important for us to pause for a minute and review the states of matter. You've probably been learning about the states of matter from a long time ago, but it's always good to remember. Okay? So for a solid, you're going to have a definite shape and a definite volume. So if we were to draw a picture, you would have, switch back to my other drawing tool. I forgot I should leave these words out. You don't need to write the words in the up close view. That was just reminders for me of how to draw this for you. But if we had a solid, you can imagine solids have atoms that are connected to each other by very strong bonds. So what happens is they tend to be very rigid and they're like connected sort of like this. Okay, connected to each other through all of these bonds, which means it's very difficult for the atoms to move around each other. Just think about if you were standing in a grid like this and holding on to the shoulders of the people next to you, how difficult it would be to change your shape, right? And those bonds hold them together so their shape doesn't change and their volume doesn't change. They always take up the same amount of space and they always have the same shape. So I always use the example of my stapler. If I take my stapler out into the hallway, it doesn't change shape. If I put my stapler in a Mickey Mouse shaped vase, it doesn't change shape. If I go into the gymnasium, the stapler isn't suddenly taking up more space. It is a solid because its shape and its volume always stay the same. As we move over to liquids, they have the same volume, but their shape is able to change. So they have a definite volume, but no definite shape. So if I was to draw you an up-close version of that, then you would have these atoms, the same atoms as before, but now they're more loosely arranged, okay? Which means they have the ability to move around each other much more easily. So picture yourself again standing with a bunch of your friends in a large group. Okay, so like maybe you're in line to get into a concert and there's a whole bunch of you, okay? They can funnel that group of people into a very small space and then into a very big space because you're able to move around each other. So what's happened in order for an atom to go from, or in order for a substance to go from being a solid to being a liquid, enough energy has to be added for some of those bonds to break and loosen so the atoms begin to be able to wiggle around each other. However, they don't yet have enough energy to get away from each other, so their volume is going to stay the same. If I have half a cup of water and I pour it into a Mickey Mouse shaped vase, it will take the shape of Mickey Mouse, but I will still only have a half a cup of water. The volume isn't going to change. So that's how you know something is a liquid. Then if we have a gas, gas is that final state of matter, okay? And these have no definite shape and no definite volume. So if I was to draw them for you, you'd have all of these little atoms, and they're out far enough away from each other that their attractive forces are really weak. So sometimes we might draw them as like a dotted line. But they're not super attracted to each other, which means not only can they move around each other freely, but they can also move away from each other freely. So if I have a 2-liter bottle of hydrogen, and then I go out into the gymnasium and I release that 2-liter bottle, not only will the gas no longer be shaped like a 2-liter bottle, but it will expand until it occupies that whole gymnasium. There's going to be a lot more distance between the particles, but it is going to expand out to that volume. So they have no definite volume and no definite shape. Their volume and their shape are both entirely based on their container. This sometimes confuses people because they say, well, I can't take a 2-liter bottle of oxygen and put it in a room with no oxygen and suddenly have, a room full of oxygen. And it's like, no, because the number of particles of oxygen doesn't change. They just spread out to take up more space. Their volume is technically larger because they take up more space, but the density would go down because there would be fewer particles for that larger space. Energy loss or gain is the cause for changes between states, just like it causes other reactions to take place. So remember, I said in order to go from being a solid to a liquid, you have to put energy in enough to break some of those bonds, loosen things up. Even more energy needs to be added to go from a liquid to a gas, and that's how you would break those bonds enough that they would move further and further apart from each other. And then the opposite would be true if we're going back down. So you would lose energy to go from being a gas to being a liquid, and from a liquid to being a solid. Matter's not always a pure substance. It can be mixed. Here is a flow chart to help you through the steps of determining what type of matter you have. So to start with, in this top box up here, didn't mean to click on the page. In this top box up here, we have all matter. And the first question you're going to have to ask yourself is, can it be separated? Can I separate this substance? If the answer is yes, I can separate it, then you have a mixture. If the answer is no, I cannot separate it, then it is a pure substance. Okay? Now, the methods we determine to use for separation is usually separating it by hand, separating it using a filter, or separating it using evaporation. So a fruit salad would be a mixture you would definitely be able to separate by hand. You'd be able to remove the grapes and then the strawberries and the bananas and so forth. Okay? If you had a mixture of sand and water, you would separate that with a filter, right? If you pour it through a fine enough filter, the sand will be left behind and the water will flow through the filter and they'll be separated. And then evaporation is that third method where you have to use heat to remove one of the substances. So think about salt water. If I boil a pan of salt water, then the water evaporates off and the salt is left behind and I've separated it. Then, once you're over here looking at mixtures, the next question you ask yourself is the composition uniform? So if it is a homogeneous mixture, like sugar and water, then the composition is uniform, meaning that no matter which portion of it I take, I have the same spread of salt and water, or sugar and water. It's spread evenly throughout it. If it is a heterogeneous mixture, like a fruit salad, then the ingredients are not evenly distributed. It would be possible for me to take 2 cups of fruit salad and have a different amount of bananas and a different amount of grapes in each cup. Okay? So that would be a heterogeneous mixture. A homogeneous mixture, it should be evenly mixed. If you've ever seen a slab of granite, you'll know that there's little pieces of different rocks in the granite that you can visually see, right? But they're not spread out in a nice even grid where it's the same amount of each type of rock in each area. So that's why it is a heterogeneous mixture. On the pure substance side, you're going to ask yourself the question, can it be decomposed by ordinary chemical means. So that means if I use a chemical reaction, can I break it apart? This isn't the same as separating a mixture, because to separate a mixture, you can do that physically without changing the substances. If you're breaking down a substance, then you're going to have to use a chemical reaction. If you are capable of breaking it down, then that was a compound. It was water or salt or sugar, which can be broken down into their elements. If you try to separate it and you cannot, then that means it is an element. For example, gold or aluminum or oxygen or chlorine. All of the ones on the periodic table, okay? You can't separate it because it's as pure as it's going to get, okay? Now, we know that there are subatomic particles, but that goes way beyond ordinary chemical means to break an atom down into its subatomic particles. Okay? Important differences between substances and mixtures. There's two important ones I want to highlight before we finish up here, okay? 1, every sample of a given pure substance has exactly the same characteristic properties. Okay? So this goes back to if it's a pure substance, it's going to be exactly the same every time you take a sample. For example, every sample of salt reacts with chlorine, but not all fruit salad has the same flavors. So basically, what we're trying to drive home here is it doesn't matter where I got the sodium from. Okay? If I dug sodium metal up out of the ground, or if I chemically separated salt to get the sodium, all samples of sodium are the same. They behave the same and they do everything the same because that's a pure substance. But if you have a mixture, then your samples can be different and they can behave differently. 2, every sample of a pure substance has exactly the same composition. Okay? So that means if I have a molecule of sugar, it always has 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. It doesn't matter how much potato I put in a potato salad, it's still potato salad. But if I change any of those amounts, if I had only 5 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms, I would no longer have sugar. It would be something different. So, another important difference. That is it for the notes for today. I would recommend you take a look at those objectives and ask yourself if you are comfortable doing each of those objectives. And then you can go ahead and get started on your homework for the day. Your homework is on page 18, and it's numbers 1 through 5.